I spent 17 years at Stanford, 7 as a student and roughly 10 on the faculty. And when I left at the advanced age of 35, I left because I thought that was my only opportunity to perhaps take another job. After that, I would be too old to make a move. So I spent half of my first 35 years on this campus. And then I spent the next 35 years at a single company, Intel. So I spent half of my life at Intel and half of my first 35 years here. So I thought I'd talk a little bit today about the first 35 years, or mostly the second half of the first 35, and then some observations of significant things that took place. And then I'll talk a little bit about my 35 years in the semiconductor industry and a few observations of some fun things that happened there. I am a recovering academic, so I don't use PowerPoint anymore. And you're just going to have to listen to me and give examples. But I thought I would kind of start off by how I ended up on the farm. I grew up in a small town called San Carlos, which is about 7 miles north of here. Went to high school there, and I was kind of enamored with the outdoors as a kid and hiked back in the Sierras. And I wanted to be a forest ranger, and that was the only thing that I wanted to be. And my senior year at Carmont High School, I applied to one school, and one school only, Oregon State University, because they had the best forestry department on the West Coast. And they're also cheaper than Stanford. And I came from a kind of a lower middle class family, so Stanford was unattainable. But I had a math teacher who taught me 4 years of math at Carmont High School. And he apparently did a pretty good job, because my freshman year at Stanford, I don't think I went to a single math class, and I got A's in all of them because they were just a repeat of the 4 years of math I had at Carmont High School. But Mr. Crawford one day came to me in my senior year and he said, Craig, you're pretty good at math and science. Here's an application to Stanford, fill it out. And I said, Mr. Crawford, I want to be a forest ranger, and Stanford doesn't have a forestry department, and I've already applied and been accepted at Oregon State. You're pretty good at math and science, Craig, fill it out. It was still my teacher, and the grades in your senior year still count. So went back of the classroom, dutifully got my pen out and started to fill out my application to Stanford that he'd given to me. And I got to this point where it said prospective major. And I said, I can't put forestry down. So I elbowed my good friend, Tom Hessler, who went to high school with, and sitting next to me, I said, hey, Tom, you're going to go to San Jose State. What are you going to major in? I think you're going to major in engineering, right? He says, yeah, metallurgical engineering. And I said, what's that? And he didn't really know what it was, something to do with metals. I said, okay, how do you spell it, 1 L or 2? So I wrote metallurgical engineering down for my prospective major, and I sent this thing off, and I was still going to be a forest ranger, but at least I could tell Mr. Crawford that I applied to Stanford. And fortunately or unfortunately, I was probably the only prospective freshman at Stanford that wanted to major in metallurgical engineering. And there was an international nickel company scholarship, and it paid for my tuition. And I don't know how I paid for room and board the first couple of years, but we made it. And so that's how I majored in metallurgical engineering. And fast forward from that time, 60 years or so from then, I'm now retired. I own a couple of ranches in Montana. One's a big cattle bison ranch. So I have my own forest today. And today I am a forest ranger. But there was a lot of stuff that happened in between. But I picked out 5 observations of my time at Stanford, and then 5 observations at my time at Intel, and I would like to just kind of go through them for you. The first engineering class I took at Stanford was Mechanical Engineering 1. And there's a couple of people in the room I know that took this course. It was basically a course in forging and welding. And it was a 2-unit course taught by a gentleman by the name of Robert Simpson, 1957. And it was a very interesting course because we did foundry practice and forging and electric arc welding, oxyacetylene torch welding of aluminum, and things like that. And in the process of taking that class, I made 3 objects. I made a bronze sundial after Robert Browning's poem, Grow Old Along with Me, the best is yet to be inscribed on the sundial. I made a cast iron foot scraper, or boot scraper. It was a dachshund dog about this long with a sharp ridge on its back that you could clean the mud off your boots. And I made a steel chisel because part of the course was practical heat treating. And I was sitting at home in Phoenix the other day thinking about this talk, and I said, I wonder what those things are worth today. And so I go online, and by golly, the sundial, there are a lot of people make that same bronze sundial, and it costs about $80. The foot scraper, I found almost an identical cast iron foot scraper for $42. And the chisel, you can get at any one of Lowe's or Home Depot for about $20. So a total of about $145 in today's dollars worth of things that I made. That year, 1957, tuition was $250 a quarter. It's gone up. But I said, hey, I got $145 worth of goodies out of this class, and $250 a quarter for tuition. It was a 2-unit course. It took about 16 units a quarter, so you divide 250 by 8, you get about $30 that was paid to do this forging and welding class. And even if you put rate of inflation, which is from 57 to 2019, is about 9x, it's about $270 that I paid in today's dollars, and I got $145 back in goodies. I doubt if Stanford offers another course that valuable to the students. By the way, I also did look at the rate of inflation of tuition between 1957 and 2019, and it's not 9x, it's 70x. That's probably a message to the administrators at the university. So that was a great observation. It was a great course because it really taught me what metals were all about and practical heat treating. You could change the properties of metal by thermal cycles. And if you've never pounded a cope and drag and this oily sand to make a casting, it's really cool stuff. I did that, so I was a metallurgical engineer at the time. The second observation was the most valuable course I took as an undergraduate at Stanford. And I hated it, absolutely hated it. It was a course in statistical theory, Introduction to Statistics. It was taught by a mathematics professor who was not interested in any practical applications of statistics, but just the proof of the theorems and such. And it was a drag, and I didn't do well in the final, but I passed. But it, in fact, has probably had more influence on my life than just about any other course I took. Because obviously you do research, and you analyze results, and you analyze the statistical significance of your results. But you do way more than that from a statistical standpoint. You read the newspaper, you watch television, you listen to politicians, you listen to noted people talk about subjects. And 90% of the time, they're talking without any statistical significance. When you read the newspaper monthly and you look at the unemployment rate, which is a hot topic today, and it goes from 3.4 to 3.3%, no one ever says the accuracy of this measurement is plus or minus such. They all say, oh, the trend is down or the trend is up. You look at the valuation between different currencies. You look at climate change. You look at just about anything. And the press, and I firmly believe this, the press to a person does not understand statistics and statistical significance at all. But everything you read and hear on the television is, in fact, stated as fact when it probably has zero statistical significance. But that course really came alive for me when, fast forward, when I was at Intel, and in the late 1980s, we were competing with Japanese semiconductor companies, and they were noted for their quality, and they were beating the ears off of all the US semiconductor companies. And I led several missions to Japan to study manufacturing technology there, and I kind of learned very quickly that it wasn't any magic. They were using simple statistics for statistical process control and quality control and design of experiments and things of that sort. And by the way, design of experiments in the semiconductor industry, when you have about 200 process steps, and each one of those process steps can influence the final electrical characteristics of the circuit, you have about 200 variables, and when you design experiments, it's pretty clever what you can do by trying to hold one thing constant and keep or hold everything else constant and change one variable. But what we found was, after all those Japanese trips, coming back, we applied the same sort of statistical process control, et cetera, at Intel. And one of the most rewarding things in my life was, after spending 2 or 3 years going to Japan and seeing what they were doing, we started to have a constant flux of Japanese semiconductor execs coming to Intel to see what we were doing, because we were back running at higher yields and better quality than they were. So that statistics course, even though I hated it at the time, I deemed to be the most significant course I took as an undergraduate. Sorry, material science. The third observation I had, and I think the prior presentation showing all those great images and such, was I arrived at Stanford at a time when instrumentation was just starting to have an impact on studying the structure of materials. You know, prior to that, we would cut up a little piece of metal, we'd put it in a little press and put some bakelite powder in, and you'd heat it up and compact the bakelite around the thing, and then cool it off and eject it, and you sand the surface down and polish it and look at it in the optical microscope. And that was the structure of materials, metallurgical structure of materials. I did my PhD, which Bill Nix knows well because he was one of my lead thesis directors, looking at dislocation etch pits and iron 3% silicon and high temperature deformation, the influence of temperature and stress and all this stuff. I must have looked at 60 zillion dislocation etch pits, and that was the structure that I was looking at. Turns out if you 3% silicon with a little bit of carbon, when you cool it down, all the carbon precipitates on the dislocations, and you etch it in a careful way, and each dislocation emanating at the surface, you get an etch pit. You can look at dislocation densities, substructure, all sorts of cool stuff. But a whole lot of new instrumentation was just coming forward at that time. You saw an earlier photograph of me sitting in front of a transmission electron microscope. The TEM starting to come out at that time. Scanning electron microscope starting to come out at that time. Field emission microscopes are coming out at that time. X-ray topography, which is looking at dislocations in silicon wafers, was basically coming out at that time. And this really opened, oh, I'd forgotten, electron microprobes. So Vic Bacris, guy's job I took before you took my job, had an electron microprobe at Intel and was basically a leader in that field in developing that tool and looking at concentrations at the micron level. So all of that just led a wonderful explosion to the meaning of structure properties. You could look at structure in a whole new scale than are the previous metallurgists who were around. That has an offshoot story, too, because a different degree of instrumentation started to come forward in the material science and engineering department, and that was computational structure. And I asked Harry Saxon, who I went to school with, if he remembered the Frieden STW-10 electromechanical calculator. Bill, you probably remember these things. It's basically a 4-function machine about this size and a whole bunch of gears and such in it. And if you were doing complex calculations, you could do that because it was more accurate than a slide rule. That was the computational infrastructure when I was a student here, basically. There was a mainframe, but no one used the mainframe. There was no scientific calculator. There was a slide rule, or that Frieden calculator. They went out of business in 1974. By the way, I went online as well. You can buy one of these calculators on eBay for about 20 bucks if you want one. They still work, I'm sure. Frieden was put out of business by electronic calculators. And I didn't know it at the time when I was playing with this machine at Stanford, but this company called Intel designed something like a 4-bit microprocessor, the 4004, which went into a Japanese calculator made by Busicom, basically a predecessor to the HP 35. But that was the forerunner of electronic computation that the common person could play with. But all these other instruments just were blossoming in the 60s. And that was, I think, it led to an explosion in excitement about the whole concept of structure and properties of materials, because you could really look at the structure other than in a metallographic sample. The fourth observation I made, looking back, was at that time, Stanford was at the center of Silicon Valley when the name fit. And that means Shockley transistor started in 1956. Fairchild started in 1957. Intel started in 1968, and a whole flock of others at National, AMD, VLSI Logic. A ton of silicon startups were here. And it was an exciting time because they were actually making something. I remember, and I took solid-state thermodynamics, Professor Stevenson, or Dave, took us off to Shockley transistor to see what these new things were. They were working with silicon boules, which were anywhere from a 1/2 inch to 3/4 of an inch in diameter, and slicing them up. And what diameter it was just turned out what that slice was, because the boule was kind of wavy along the outer characteristics. They're making individual transistors, and Bill Shockley gave us a talk, and I kind of got interested in that stuff that time. And after that, I did some consulting at some of the semiconductor companies, Fairchild and National and others. And it was a real revelation to me because I was more or less trained as a metallurgical engineer. I never forgave the department for changes named a material science halfway through my degree. But I do have a diploma which says Bachelor of Science in Material Science, parentheses, metallurgical engineering. So someone felt bad about changing the name. But if you were working with metals, as I was at that time, and you were looking to create a new metal, a new alloy, a new something, it was multiple years to try to do something to get it put into production, and new steel, new aluminum alloy, new titanium alloy, etc. And just a little bit like getting a drug approved by the FDA today. The semiconductor industry, on the other hand, was every 6 months came out with a new product that obsoleted the prior product. And so that just was kind of exciting. If you were an associate professor getting a little bit bored with doing basic research, and don't take this personally, folks, but I was doing basic research in a few areas, and there were half a dozen or dozen people around the world who were doing research in those areas, and we all knew each other, and we all read each other's papers before we were published. And So publishing didn't get to be that much more fun anymore. I had tenure. I wrote a textbook with Bill Nix and Alan Tettleman, and so all of a sudden, the idea of practical application of this training got to be very exciting, especially if you could put products in the marketplace in 6 months or so. So I did. I took a year's leave of absence from Stanford, went to Intel, and kind of stayed. It turned out the stock options were better there, too. The last observation I had, and this was not an observation which was publicized by the deans, either the head of the departments or the dean of the School of Engineering, but has been true for decades and decades, is that the most common educational background of a Fortune 500 CEO is why would I be asking that question in front of a bunch of engineers? It's apparently still not common knowledge. But it's engineering. And now, it may not be their only degree. I mean, a person may have gotten a bachelor's degree in engineering and an MBA, but the most common educational background of a Fortune 500 CEO for decades has been engineering. And there's a very simple explanation for that, in my opinion, which is engineering is really a problem-solving education. And you use problem-solving methodologies, and you use data, and you use statistical significance, you use a lot of stuff to solve problems, which are fortunately applicable to all sorts of problems: personnel problems, marketing problems, competitive problems, production problems, whatever problem you might have. So I think I got, and those of you who are either in the Department of Material Science or in engineering, I got the best possible education for the business world, even though I've never taken a single business course. And that was problem-solving technology. And the same sort of problem-solving technology you use on a scientific or engineering problem is equally applicable across the board. So I want to thank Stanford for that education and help me in my later life. But apparently, you guys still don't publicize that aspect. You might have a bigger undergraduate class than the 15 students if you did. But so those are some observations about material science in the old days. That was 1957 to 1974 that I was here. So then I turned 35 and I left. And I joined this startup company. They weren't really a startup, they were an established company. Intel was about 4 or 5 years old at the time. I knew a bunch of the people because a bunch of people from Fairchild, which I'd been consulting at, went to Intel. And one day I received a phone call saying, did I have any graduate students who knew anything about ceramics? Because ceramics, aluminum ceramics packaging was the common packaging material for integrated circuits. And I responded a little bit frivolously on the telephone to the gentleman who called me. He said, no, we don't have any students who know anything about ceramics, but how about a frustrated associate professor? And the next thing I know, I was down interviewing Bob Noyce and Gordon Moore and Andy Grove and a bunch of people, and I went. So here are now 5 observations on time at Intel related to material science, primarily. The first observation is pretty obvious. It's Moore's Law. And Moore's Law is empirical finding from Gordon Moore. He published a paper in 1965 doing a semi-log plot of the number of transistors in an integrated circuit over time, and he found it had a straight line and found it basically doubled every 18 to 24 months. And in the paper, if you've ever read the original paper, it basically, Gordon says, nothing doubles forever, so this can't continue. this probably can't last another 10 years, but it's an interesting observation of the rapid growth of the industry. By the way, at the time I joined Intel, their first commercial device was a 64-bit DRAM, 64 bits. And the product that really put the company on the map a year or two later was, in fact, a 1,000-bit DRAM, the 1103, which became an industry standard, replaced magnetic core, and put Intel and the semiconductor industry on the map. But Moore's Law basically said doubles every 18, 24 months, and forecasted in 65, 75, Moore's Law was still happening, 85, Moore's Law was still happening, 95, Moore's Law was still happening, 05, Moore's Law is still happening, 2015, it's still happening. It's struggling. It's more difficult today to double the number of transistors or to have the size of the transistor than before. And we'll talk about that in a moment. But there's still life in silicon. That brings me to the next interesting observation. Moore's Law was kind of a roadmap for the whole industry at the time. The next observation was about the advances in lithography. And you wouldn't think lithography has much to do with material science, but when you start to worry about photoresists and patterning and imaging things, it gets exciting. And one of the excitements is when I first started in that business, the mid-70s, the circuits were a few microns in size. You could see them with the naked eye easily. There was a rule of thumb at the time that if you were doing lithography work, basically just doing printing an image, that the resolution of the image you printed couldn't be much more than the wavelength of light you were using. And the visible or near visible stuff is about a micron. So there was this concept that, when you got down to a micron in dimensions, this visible light or near visible photolithography is not going to work. Well, the industry hired a whole lot of smart engineers, both in optics and in photoresist technology. And the near visible light images didn't stop at a micron. They didn't stop at a tenth of a micron. They're now at 100th of a micron, or 10 nanometers. And there's still some life in that horse yet. All you have to do is figure out how to make extended UV. Extended UV is a politically correct term meaning X-ray. X-rays are not only dangerous, but X-ray lithography was going to be the savior of the industry 40 years ago, and it didn't work out, so it was deemed that when you talked about X-rays, you would talk about extreme UV or long X-rays. That would be politically correct. And people are still working on that technology, and that is the next generation of lithography. But it's quite amazing that the rule of thumb was exceeded by a factor of 100 in terms of near visible photolithography work, and taking circuits from micron or so to 100th of a micron or so. Great advancement, great challenges, great equipment, expensive as all hell, but it works. The third area of excitement, and mentioned a little bit in the introductory speech, was the transistor structure. And the workhorse of the industry forever has been the CMOS transistor, planar CMOS transistor. And on silicon, gallium arsenide has been forecasted to do away with silicon a number of times, and silicon nitride, all of the compound semiconductors. Nothing matches the cost performance of silicon. And the amount of money that has been poured into silicon is quite impressive. And until nature stops its advancement, I don't think any other technology is going to get in its way. By the way, just as an aside, when I left Stanford my idea of success as a researcher was to have a couple $100,000 a year research budget and maybe a $50,000 a year capital budget. When I retired at Intel, we had a $10 billion R&D budget, a $10 billion capital budget, and a couple $1 billion marketing budget about Intel Inside. So there's a lot of money being poured into this technology on an ongoing basis, but it is still, in fact, provides a pretty good return on investment. So the silicon transistor is struggling. There are two options: replace it or go three-dimensional. You see a form of three-dimensionality in terms of silicon. How many of you have a film camera? Do you use it? But the flash memory cards you get are basically a three-dimensional stacking of thin slices of flash memory in it. And that's a three-dimensional structure, and that's how you can put all those gigabits and gigabytes of memory into that small form factor. So three-dimensionality you can do by stacking circuits, or you can, in fact, figure out how to build a three-dimensional transistor array as opposed to just the planar transistor. So you can figure out how to extend the silicon transistor's life, or you can replace it with, and there's a lot of research going on, hot areas probably, quantum computing and quantum dots and things of that sort. And they have some very unique characteristics that they could do things like crack security codes almost instantaneously when they are put into practical use. But the interesting thing there, as far as I think the opportunity is concerned, is there's a whole new raft of materials, a whole new raft of production techniques, architectures that go along with quantum computing. So I kind of look at quantum computing like silicon was in the 1950s and 60s. In the 1910s and 20s, quantum computing is an opportunity. The fourth area of interest, and I was talking with someone earlier about this who worked at Intel and was involved in metallization structures. And an image of a cross-section of an integrated circuit was shown on the slide earlier with about 10 layers of metallization. And the reason you get these multi-layer metallization structures is, in fact, when you have a couple of billion transistors and you're trying to electrically connect everything, you can't do it with a single layer of metal. You have to stack layers of metal and have vias go down to contact different transistors or transistor structures. And the world moved a long time ago from single-layer aluminum to multi-layer copper metallization with tungsten plugs. And the way this has happened is, I think, nothing short of phenomenal. You all know that you build transistors in clean rooms because any dust particle on the surface destroys the next photolithography effort. And you take great care not to put anything in touch of the active surface of the silicon wafer, except you have to put the metallization layers on top of that. And you have to do this in a planar fashion because once you get steps, no matter how you put the metal down, metal doesn't accurately cover the steps, and you get cracks and stresses in it and so forth. So the way that we put 10 layers of metal on top of the active silicon layer is, in fact, you put one layer down and basically pacify it, and then grind it flat. Grind it flat. The same way that I was taking these metallographic samples on this little polishing cloth and some alumina polishing compound on it and make a nice, shiny, smooth surface. The industry does that routinely with 12-inch diameter wafers. And by flat, we're talking a fraction of a micron flat across all 12-inch diameter because you don't want to grind it more on one side than in the center on the other side. This was created by IBM, and when they first announced this technology, all of us who thought we knew something about materials said, this is crazy. This will never work. It's impossible. These guys are crazy at IBM. And somehow it worked, and it is a standard operating procedure today. And it is truly an incredible feat to do 10 successive polishings on that active surface area and get the dang thing still to work. Truly a metallurgical wonder, and it's good. I did a lot of my thesis work on copper, and they use good copper in that, and tungsten or wolfram, whatever you call it, is the plug material typically in the vias. The last thing that I found was extremely interesting in the semiconductor industry is when I joined it and Intel was making dynamic RAMs, the 1103, they were about 1 square centimeter in size roughly. It cost about $1 to make a good circuit piece of silicon. So $1 per square centimeter was about the rule of thumb. And that 1103, that had roughly 1,000 transistors in it because it was basically one transistor memory cell. So $1 per square centimeter for 1,000 transistors. You now had to take that piece of silicon and you put over 1 billion transistors in it and 10 layers of metal on it. And how much does it cost to produce? Not sell, but produce. There's a subtle difference there. About $1. About $1. And it's been a phenomenal journey, materials journey, to make that happen. In fact, you've basically decreased the lineal dimensions of what you're printing by a factor of a couple hundred. You're putting 10 to the 6th more active circuits on the chip of silicon. You're still doing batch processing. You've increased the wafer size, and because it's batch processing, if you increase the wafer size, you decrease the cost of processing a batch in terms of the area involved. But you still have to print this silly little circuits kind of one at a time. But it's been a truly amazing adventure to, in fact, get that sort of cost reduction. And that's what allowed you all to have cell phones that you're punching into right now. That's what has allowed you to get petaflops of compute power. That's what has allowed the whole computer revolution, internet revolution to take place. And it's kind of interesting when you look at what that impact has had on the world's economy, especially the developed economies of the world. There were really 3 things that kind of happened in parallel. And I used to give talks about this in the late 1980s and 1990s. And when I was giving my standard marketing pitch for Intel Corporation, I'd say, just imagine what you could do if, in fact, you have free computing power on the one hand and free communication costs on the other hand. And in fact, the two were actually going in parallel at that time. People were figuring out how to push more and more photons down a glass fiber. At the same time, they were putting more and more transistors on an integrated circuit. So the cost of communications came down exponentially, the cost of computing came down exponentially. And I used to say, hey, just think what you can do with free MIPS, free bauds, and also something that goes with it, which is Metcalfe's law, and you're familiar with that, which is the value of a network goes as the square of the number of nodes in the network. So more and more people connected, the free communications capability and free compute power. And we weren't smart enough, we were just selling compute power. We weren't smart enough to do the Facebook, Google thing, which is in fact take advantage of the infrastructure that we were putting in place. Well, 40% of the world's economic growth or so, the last 50 years, has been free compute power, free communications capability, and that network that exists. So, having said that, what are you guys going to do for the next 50 years? And everybody has their idea of what to do for the next 50 years. The national academies have their grand challenges in the U.S. The Japanese have their grand challenges, which are the functional equivalent of our national academies in the U.S. The Russians have their grand challenges. The Europeans have their grand challenges. The Chinese have their grand challenges. A lot of those grand challenges have materials at their center of action. You saw examples of some of those earlier. I think there's still three of the grand challenges that are absolutely key going forward. One is, you guys can't let me down. You got to keep Moore's Law going. When I was at Intel, we made the first teraflop computer with 10,000 Pentium processors in it. Now you get a teraflop out of a single processor. So now we're into the petaflop range, and I know what the current record is, roughly 100 petaflops, something like that. And we're looking at exascale, 10 to the 18th floating point operations per second. You got to keep that one going, because the world is absolutely hooked on rich data, big data, analyzing data, and doing, hopefully, good things with it. By the way, who was the first AI innovator in the world? You guys obviously do not read the Wall Street Journal. You read technical journals. Company called Walmart, a company that is a computer company masquerading as a retailer. What did Walmart do? Walmart had a central processing system where every store was connected to every line item that was sold, analyzed overnight, adjusted pricing, adjusted the distribution of goods to where they were selling from where they weren't selling, so forth. What better example of AI is there? Done on mainframes, by the way, but intelligent point of sale terminal. But people are hooked on this stuff, and you can do great stuff with it. So you got to keep Moore's Law going. So you got to find a new switch. Because I'm beginning to believe that the planar CMOS transistor is, whether it gets down to a micron or, a nanometer or what, signal to noise ratio eventually kills you. You got to have a different switch. So new materials, new switch, integrated in. You can use the existing metallization structure on semiconductors, because you're still going to have all this information flowing to different parts of the circuit. So you can use all that metal stack that we've already got going. But you need a new switch. Please find the new switch. You also need to keep the free communications capability going, because you want to move rich data around. You got to move a lot of photons or electrons around. So both wireless and fiber communication needs to have continued advance. And those are really the two fundamentals, along with Metcalfe's law, that can continue to drive excitement. But fundamentally, they're both materials problems down deep. So find me a new switch. Continue the functional equivalent of Moore's Law on communication. And, Facebook will then not have 2 billion users. They'll have 6 or 8 billion users and rapid communication back and forth. And if any of you put your personal information on Facebook, you're crazy. But there'll be a lot of excitement going. The one that I'm really kind of interested and excited about, though, is the alternative energy program. And not so much on, the next percent efficiency on solar cells, but the 24/7 part of alternative energy. There's only one form of green alternative energy that I know that nobody else is interested in, which is with the advent of drilling technology. And if you do the mathematical calculations, you can drill down, not frack, but drill down and then go horizontal off a very small footprint. You can do the mathematics to how much heat you can collect from the earth in a hot spot on the earth. Just bring that up, turn it into steam, and run it through a standard steam turbine. That's a 24/7 alternative energy. You don't need the sun to shine or the wind to blow to get 24/7. And it's also a very small footprint, but no one seems to be interested in it. People are more excited about big solar arrays, either photovoltaics or mirrors and heating steam. But in all those processes, you need to have storage, and you need to have better battery technology. And we all need better battery technology because we get frustrated having to charge our phones on a daily basis anyway. So battery technology is a classic material science problem. And it was mentioned in some of the studies on in the material science area. Bob Huggins did some great work on this years ago in ionic and electronic transport solids. It's a great interdisciplinary program. I can't emphasize enough or support enough the concept that material science is interdisciplinary. It's structure and property materials. You have to get somebody who really knows the structure associated with someone who knows how to use the properties that you get out of it. So battery technology, a new electronic switch, and communications technology, both wired and wireless, I think are absolutely key. I want to echo the conclusion on the last slide that you saw, which was I'm equally optimistic about material science and the next 50 years. I think you are key to go off on another 50 years of excitement, just like the last 50 years that I've witnessed in this valley. And if you get frustrated, just remember, your engineering degree will suit you well to become a CEO someday. Thank you.